My project seeks to model lunar craters. More specifically, I am creating a model that simulates lunar craters with respect to time. My research advisor is Professor David Kipping, a prominent astrophysicist specializing in the field of exoplanets. He has been an absolutely phenomenal mentor, and I am very grateful for this opportunity and all the skills I've gained throughout the process. Once completed, this lunar crater model may have many applications. It may be applicable to exomoon research and could help determine potential areas of habitability. It can also be used to determine the survival rate of an object on the moon, whether that be an hypothetical alien artifact or an interstellar meteor. There is also a mission that will be sending a time capsule to the moon. We would be able to calculate the time before it is likely destroyed. Finally, in the future, we will be able to have moon bases with people on the moon. This lunar crater model can aid in calculating the safety and survival rate of the moon base. My main lunar crater simulation has multiple components. First, I generated a cratering rate lambda based on exponential decay. Then I generated random latitude and longitude for each new crater. I generated the size of the crater using the inverse CDF, which is a sampling technique. It has 10 time steps and spans over 2 billion years, with each time step representing 200 million years. After I completed my main lunar simulation, it was time to move on to the crater erasure. Crater erasure is a crucial concept in my research because as craters form over time, they overlap each other, and craters that are overlapped by another crater are erased. So I must incorporate crater erasure in order to complete the lunar crater simulation. By far, the greatest challenge in this project has been the crater erasure code, specifically the code that determines if two craters overlap. The issue is that while the overlap function would determine if two craters overlapped, it was shown in the plot that they didn't overlap. Essentially, there was a discrepancy between the plotting of the craters and the crater overlap code. The problem was very troubling, as it wasn't clear if there was an issue with the crater overlap code or the plot. The code itself is relatively simple. We calculate the distance between the centers of the two craters and see if this distance is greater than the length of the radii combined. Plotting craters should be relatively simple. Plot a circle with the given center coordinates. Why wasn't it working? Eventually, I was able to determine that it was my crater plots that were inaccurate, and not my crater overlap code. For my test case, I used two big craters with a diameter of 500 kilometers. I started them at the same point and moved one of the craters by 5 degrees longitude each time. I used NASA's lunar distance calculator to determine the distance between the craters and manually determined if that value was greater than the radii combined. I found that the crater overlap code worked with 100% accuracy, even for small increments. This meant that there was an issue with the crater plotting. While this was a beacon of light, it was frustrating to reckon with how much time I had spent analyzing the crater overlap code to determine its accuracy. It was tedious work, but I gained many skills throughout the process. To fix the crater plots, the first solution I tried implementing was plotting them in 3D, instead of 2D like I had initially. I thought this was a solid technique, but it was difficult to determine from the plots whether or not the craters overlapped. So I decided to continue searching for a 2D alternative. I tried about 10 different projection methods. I narrowed it down to the best two and computed my test case. While it worked for many cases, when I got closer to the boundary of overlapping and not overlapping, eventually failed. I also tried a different method of plotting the circles, by using a function that creates a circle based on a given radius and centric coordinate. Unfortunately, this also didn't improve the accuracy of the plots. I attempted many solutions that didn't lead to more accurate results, which was ultimately quite frustrating. In response, I consulted with many people extensively, especially in the realms of computer science. I had tried everything I could think of, and everything the internet said to try. What more could I do? After weeks of working on this problem, I had another idea. If my crater overlap code is working, clearly it is able to spatially orient the craters and create results that reflect this spatial orientation. I decided to include the crater overlap code into the crater plotting function. Luckily, this was a success. Not only did I compute 10 test cases for my original test craters, I performed more tests on 2, 3, and 4 crater systems. It was completely accurate. I was very happy and eager to move on to the next part of the simulation. The next step in the simulation was the rim loss calculation. The rim loss function calculated the rim loss on crater 1 due to crater 2. It does this by calculating the central angle between the crater centers using the spherical law of cosines. Then, using the formula for intersecting circles on a sphere, it calculates the angle subtended by the arc of the crater 1's rim that is intercepted. From there, it converts that angle into a percentage of the circle. That percentage is the rim loss on crater 1 due to crater 2. Finally, I can create my crater survival function. This code will take in a CSV file with longitude, latitude, diameter, and time step, and will output a CS file with the surviving craters only. For a crater J, it creates a subset of craters that overlap with crater J and are formed after J. Then, it calculates the rim loss on crater J due to each crater and adds them all up. If that total is less than 75%, it survives. It repeats this process for every crater and produces a CSV file with a list of craters, their longitude, latitude, diameter, and time step. Then it was time to test the code. For a test dataset of 1,000 craters, it took 27 seconds. For 10,000 craters, 38 minutes. For 100,000 craters, it completed 138 craters in 10 minutes, which is about 0.1%. The next step in this project will be to optimize this code so that it completes the calculation quickly. I will implement profiling, which determines how long each part of your code is taking, and focus on the parts that take the longest. I will also replace parts of the code with C and Python, which are languages faster than Python. In the end, I am extremely happy that I overcame the crater plotting issue. I am satisfied that a version of the lunar crater simulation is complete despite it taking a long time to run. I am excited to continue to refine the code and see its applications in the future of astrophysics research. I am very grateful to Professor David Kipping for being the most amazing advisor I could ask for. His continued mentorship was key to my progress. Thank you.